All right, today we're going to tackle a really cool trick in physics. We're going to figure out exactly how far something has traveled just by looking at its velocity time graph. Sounds kind of weird, right? Well, let's break it down. Okay, so take a look at this. You've got a graph showing a car's velocity changing over time. We can see it speeding up, slowing down, whatever. But here's the real question. How far did the car actually go? How do we pull a real-world distance, like in meters, out of this collection of lines? That's the puzzle we're going to solve right now. Section 1, the simplest journey. We're going to start with constant velocity. Before we tackle the tricky stuff, let's start with the absolute easiest scenario. Imagine a car that's just cruising, not speeding up, not slowing down, just one single steady speed. Now, you've definitely seen this classic formula before, right? Displacement equals velocity times time. It's probably one of the first things you ever learned in physics. Super straightforward. But the real magic happens when we see how this simple equation connects to the graph. So let's see what that looks like on our graph. We're going at a constant 10 meters per second for 4 seconds. So the height of our shape is the velocity, that's 10, and the width is the time, that's 4. And what shape do we get? A simple rectangle. Height times width? Sound familiar? 40 meters. And here's the aha moment. How do you find the area of a rectangle? You multiply its height by its width. In our case, that's 10 meters per second times 4 seconds. The math works out to 40 meters. So the displacement, how far the car went, is literally the area of the shape under the line. That's the big secret. Okay, section 2, calculating displacement when velocity changes. So that was nice and easy with a flat line. But let's be real, cars speed up and slow down. So what happens to our little area trick when the line on the graph starts to, well, move? So now look at a journey like this one. The car cruises at a steady speed for a couple of seconds and then, vroom, it starts accelerating. Our nice simple rectangle is gone. Now we have this weirder shape. So the big question is, does our area equals displacement rule still work? And if it does, how on earth do you find the area of that? Well, the answer is actually pretty clever, and it's a strategy you can use for all sorts of problems. We just break it down. We take this one complicated shape and we chop it up into simpler ones that we do know how to handle. In this case, it's a perfect rectangle and a perfect triangle. Easy. So let's run the numbers. First, the rectangle. That's for the first 2 seconds. It's 2 seconds wide and 10 meters per second high, so that's 20 meters of displacement right there. Now for the triangle part. Its base is also 2 seconds, and its height goes up by 10 meters per second. And you remember the area of a triangle, right? It's 1/2 base times height, so that gives us another 10 meters. Add them up, 20 plus 10, and you get a total displacement of 30 meters. See? The rule still works perfectly. Okay, section 3, area versus slope. And I need you to listen closely here, because this is the #1 mistake people make. It's so easy to get them confused. So let's make sure we nail down the difference between the area under the graph and the slope of the line itself. Here it is. This is the phrase you need to burn into your memory. The area tells you how far you've gone. The slope, how steep the line is, tells you how fast your speed is changing. In other words, your acceleration. Let's put it all side by side so it's crystal clear. On the left, you have area. What does it represent? Displacement. How do you calculate it? Velocity times time. What are the units? Meters. Now, on the right, you have slope. What does that represent? Acceleration. How do you calculate it? The change in velocity over the change in time. And the units? Meters per second squared. Two totally different things from the same graph. All right, our final section, your physics toolkit, the key takeaways. We've covered a lot of ground here, no pun intended. So let's wrap this all up into a few key rules you can take with you. Okay, here are the golden rules. Rule 1, area under a velocity time graph is your displacement. Rule 2, if the graph looks crazy, just chop it up into simple rectangles and triangles. Then just calculate the area of each piece and add them all up. And the big ones to remember, area equals displacement, that's how far. Slope equals acceleration, that's how fast your velocity is changing. And please always, always check your units. They'll tell you if you're on the right track. And I'll leave you with a final thought to chew on. Everything we've looked at today has been above the horizontal axis, right? Positive velocity. So what do you think a negative area would mean? What would it represent if the line on the graph dropped below that zero line? What is the car doing then? Think about it. Thanks for tuning in.